So how are you guys doing? How everyone is doing today? How are you? Good. Disconnect the disconnected to this HDMI. I did connect, didn't I? Yeah. Okay. So instead of giving you a homework on 3.3, 3.4, I'll just post a review sheet, like I said in our last class, and our exam will be 24. So the review sheet due date, it will be, let's see, 24 is exam, 1, 2. So I need next week, Thursday midnight, so I can have enough time, 21, 22. I'll have 2 days to grade, and I'll post the solution on 23rd. So you have 2 days to study.
So it's due the 19th?
9/20.
Oh, it's due the 20th.
20th. Because I want to grade before your exam, so you can have an idea how I will grade them in the exam. On Sunday midnight. I mean, so you have Sunday and Monday, 23rd midnight. No, 22nd midnight. So you'll have Sunday to study. I mean, Sunday and Monday, 2 days to study. I mean, study, review. I can do that. 20, yeah, then you have more time. Even if you didn't do this, the review sheet oil, at least you had time to learn the materials. Yeah, I'll do that actually. Once you are done posting, uploading your assignment, I'll just post the solution. Good idea. Okay, so the exam will be based on, so today is Wednesday, we are still going to do chapter 3. And my plan for next class is to start chapter 4. It will be 1.4, sorry, 1.5, 2.1, 2.2, and chapter 3. And then let's see how much you can finish on Monday. And then I'll decide, should you put the Monday materials or should skip Monday materials? But definitely it's 1.5, chapter 2, chapter 3. Definitely. And the rest of the materials, what we are going to do after chapter 3, or what will not be in exam 2, it will be in exam 3. So not exam 3, final exam. And final exam will be cumulative. So the new materials plus the old materials. Okay. Any question? Comments? Concern? No? Okay, so we were not able to do many questions in our last class from these, but these are very important, and I'll post a few in the exam. So my plan for today is to go over a few of them, and then the 2 questions we didn't have time to do at all. These questions. And then probably by the time we are doing everything, our class will be over. Question? Okay. Linear independent field. we have two vectors, 2, 4, and 4, 8. In which space R2, R3, R4? R2. So even though they did not mention that, but you already know it's R2. How do you know it's R2? 2 rows. Number of rows tells us which space, which vector space we are in. So are they linearly independent? How do you know? Good. So if you multiply, let's say this is vector 1, this is vector 2. If you multiply 2 times v1, it turns into v2. So they are not linearly independent. That asks us the second question. Then how many linearly independent vector we have? 1. Since we have 2 and they are not independent, that means one of them is the real one and the other one is the dependent one. So you have only one independent vector here. So we have one independent vector in R2. Are they spanning set for the vector space? Means do they cover the entire R2? No, why not? We need at least 2 linearly independent to span entire R2. So we need at least 2 linearly independent vectors. So what's the dimension of our span? 1. So do they form a basis for our space? Nope. Why not? How many independent vector we need? Exactly 2. We need exactly 2 linearly independent vectors if you want them to be a basis for your space. Now it's not asked here, but if you have only one independent vector, how much they cover, how much they span in the space? Like what's the geometric shape for it? A line. So the only thing they can span in the R2 is just a line that goes to the origin 0, 0. So it forms a line or it spans a line. The geometric shape of the span is just a line. And I will also ask this question. What's the geometric shape for this span? Okay, the next one. We have 2 vectors in which space? R3. So we have 1, 1, 3, our first vector, 0, 2, 1, our second vector. So let's say this is V1, this is V2. Are they linearly independent? Yes. Why or how do you know? Exactly. We cannot find a C, a constant, if you multiply B1 and it will turn into V2. It's not possible. So when you have 2 vectors, your life is easy. All you have to do is check from one point, can you go to the other point? So if you want to go from 1 to 3 or 1 to 2, you need to multiply the first vector by 2. But if you do that, you have to multiply every element by 2, but it doesn't produce vector V. I mean, the second vector, V2. So they're independent. So how many independent vectors we have? How many? 2. We have 2 vectors and they both are independent. So are they spanning set for the vector space? Means do they span entire R3? Nope. How many we need? At least 3. We need at least 3 linearly independent vectors. So what is the dimension of our span? 2. Dimension means how many independent vectors do you have? We have 2 independent vectors, so we have 2. So do they form a basis? Nope. How many we need? We need exactly the linearly independent vectors. So we have 2 independent vectors in R3. How much they cover in R3, or what's the geometric shape for the span of these 2 vectors? It should be a 2D plane that goes to the origin. So the 2D plane means XY plane, but the plane goes to the origin. Any questions so far? So this is the shape of the span. Now one interesting one. -3, -6, -1, our vector 1, 2, 5, 1, our vector 2, and 8, 14, 2, our vector 3. Are they linearly independent? When you have 3 vectors, how do we check them, whether they're independent or not? You cannot just compare one with other one. You can compare one with other one if you have only 2 vectors. For 3 vectors, that method doesn't work. Alexander, what do you do? Determinant. So I taught you many methods of determinant. Whatever is easier for you, use that. My favorite one is rewriting the first column. So -3, -6, -1, 2, 5, 1. When we rewrite our first right diagonal is 3 times 5 times 2. That gives us -15. Oh, wait, -30, what I'm saying. -30. Our next diagonal is 2 times 14 times -1. So it's -28. And then the last one is 8 times 6, 48. It's the negative, so -48. Right? 5 times 2 is 10, 30, negative. 14 times 2 is 28, negative. We have 8 times 6, 48, negative. And then you multiply by the left, not multiply, subtract the left diagonal. So first left diagonal is 8, 5, -1. So we subtract negative, negative, which turns into positive 40. The next right diagonal is -14 times 3. So it turns into positive. How much is 14 times 3? 52. 42. And then the last diagonal is 2 times 6 times 2 times -6 times 2. So negative, negative turn into positive. 4 times 6 is 24. If you add all of them, what is our determinant? Is it 0? It's not 0. It's -24, but negative, negative turn into positive. You're going to subtract every left one. So minus, 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 and all these right ones you're adding. So add the right diagonal, subtract the left diagonal. This is definitely not 0, right? If you add them, it's not 0. So if the determinant is not 0, what it tells us? Is it independent or not independent? Are they independent or they are not independent? Which one? Do you remember? Determinant is not 0. Is it a good thing or is it a bad thing? You already forgot. We don't want determinant to be 0. So since determinant is not 0, we are happy because they are independent. If determinant is 0, that means something is wrong. They are dependent on one another. So it's not 0, it's a good thing. It means, yes, they are independent. They don't depend on one, they do not depend on each other. They're independent. So how many linearly independent vector we have in this set? How many? You only have the answer on 1. On 1, we just prove that all 3 are independent. They do not have any connection. They do not have any relation. So how many independent we have? 3 of them. So we have 3 independent vector in R3. Do they span entire R3? Yes. Because we needed at least 3, and we have these 3. And what is the dimension of our span? Means how many independent vector we have? 3. Do they form a basis for R3? Yes. We needed exactly 3 independent vector, and we do have exactly 3 independent vector in our set. So this is a good one. It follows all the good things. They are linearly independent, they form a basis, they span the entire vector space. Any question? Okay, it looks same, but let's see, do you get the same answer or not? We have 2, 1, -4, 3, 2, 1, and then 3, 1, 4. 3 vectors in R3. Are they linearly independent? How do you determine whether they are independent or not? Determinant. So go ahead, find the determinant. What's the determinant for this vector, for this matrix? I mean, the matrix formed by these vectors. Why do you take the attendance? There is 11, 12. 11, 12. Brandon C. Lakes. Joseph. Not here. Justin. Not here. Gibran. Here. Shibu. Not here. Michelle. Not here. Jack. Here. Ashif. Not here. Darius. Not here. Winston. Here. Abigail. Here. Shane. Absent. Emily. Here. Kanar. Absent. Christine. Edison. Absent. Maisha. Here. Brandon. Here. Elvin. Here. Shafal. Absent. Alexander. Here. Pitila. Absent. Wanshuan. Here. And Kailun. Here. So what is its determinant? How much is the determinant? Did you find the determinant? $35. So it's not 0. Since it's not 0, that means we're going to get the same answer as the last one. So determinant decides everything else. So Yes, they are linearly independent because determinant is not zero. We have 3 independent vector. How many independent vector do you have? So determinant tells us how many determinant tells us the 3 vectors you have, are they independent or not. If you have 4 vectors and you take the determinant of 4 by 4 matrix, it will tell you if the determinant is not zero. That means all 4 vectors, they are independent. So here we have 3 vectors, determinant is not zero, means all 3 vectors you have here, they are independent, linearly independent. So that's why I need to find the determinant. It makes our life easier. It does happen. Sometimes there are only 2 independent vectors. Sometimes only 1 independent vector.
I know, like, if it's 0.
Then it's 3. If it's not 0, that means it's not 3. Then you see, do you have at least 2 of them or not? Checking 2 is easy. And then if 2 of them are not, that means you have 1 of them. So you start with 3 by looking at the determinants. So are they spanning set? Do they span in test set, in test space? We have 3 independent vectors. Yes. What's the dimension of our span? 3. Do they form a basis? Yes. Okay. This one. 2, 1, negative 2. 3, 2, negative 2. 2, 2, 0. Find out the determinant. It will tell us all the story. Jack, what's the determinant for this 3 by 3 matrix? 0. It is 0. Yay. So when you have 0, what does it mean? Are they linearly independent or they are not linearly independent? They are not. So no. That means that all three, they are not independent. That takes us to the question, well, if 3 of them are not independent, at least how many of them are independent? So you go and check 2 of them. Are there at least 2 of them independent? So what do you notice? Do you have at least 2 independent vector? To check 2 independent, it's easy. You just have to take 2 of them. For example, 2, 1, negative 2, and compare that with 3, 2, -2. This one is saying that if you want to go from 1 to 2, you need to multiply the first vector by 2. But if you do that, you're supposed to get 4, 2, -4. Do you have 4, 2, -4? We do not. So the first and second vector, are they independent of one another? Yes. So we have at least 2 independent vectors. 3 of them are not, but at least 2 of them are. And now we have 2 vectors in R3. Do they span entire R3? No. So what's the shape of their span? Means how much they span, how much area they cover from R3. The geometric shape of their span is 2D plane. It's a 2D plane, like XY plane that goes to the origin. It only can cover a plane, only X and Y axis, that's it. It cannot cover X, Y, Z, all 3 axes. What's the dimension of the span? 2. Do they form a basis? No. We need exactly 3. We had 3, but they're not independent. So they do not span, they do not form a basis for the space. So we see an example with 3 linearly independent. This example has 2 linearly independent. And now if you look at the next one, what do you observe?
Question. If they form a base, if the dimension is 3 independent vectors in R3, what's the shape of that?
Entire R3. They cover the entire XYZ plane. The R3
Every
space.
Direction?
The entire vector
Is
space.
that a solid?
Yeah, it's like a sphere.
Oh.
So when we say, do they cover entire space? If the answer is yes, that means the shape is the space, whatever space you are in, is that shape. So if you're in R2 and it spans the entire R2, it means it covers the XY plane, the entire XY plane. And if it's R3, it covers the entire XYZ plane, means the entire 3D space. Okay, the 3 vectors we have, are they linearly independent? Nope. We don't even need to find the determinant this time because it's very visible. How many independent vectors you see? Only 1 this time. How do you know it's only 1? What relationship we have between V1, V2, and V1, V3? So V1 is negative V2, and V3 is multiples of 2. So you can write them. So V2 is negative of V1, and V3 is twice V1. That means the only thing that is independent is 1 vector V1. The other 2 depends on V1. So that's why we have only 1 linearly independent vector. Since you have only 1 independent vector, do they span the entire vector space? Nope. So how much they span? It means what's the geometric shape? If you have only 1 independent vector, a line. It doesn't matter how many vectors you have in the set. If you plot them, they will go to they'll go to only 1 line that goes to the origin 0, 0. So every point you have from all these vectors, they will lie on a straight line, like this way. So I even forgot how to draw XYZ plane. One of them is here, right? Here and then here. That's how you draw XYZ, right? I didn't draw them for a while. So probably this is X, this is Y, and this is Z. So it covers just a line that goes through origin. This is their span. Means how much they cover in XYZ plane. So what's the dimension of our span? Means how many independent vectors we have? One. Do they form a basis? No. Next one is also interesting one. We did it a few lectures ago. Do you remember? Alvin does. Anyone else? Carolyn? We have 4 vectors. In which space? R3. So we know the answer for the 5th question right away. If you have more vectors than how much you need, do they form a basis for the vector space? They cannot. We need exactly 3 to form a basis for R3. We need exactly 3 linearly independent vectors. So we don't even care whether they're independent or not. When you see 4 of them, automatically the answer for the 5th one is no. They cannot form a basis. Okay, and now we go to the question number 1. The 4 vectors we have, without doing any math at all, do you know the answer? Are they linearly independent? You have 4 vectors in R3. Alexander, why not?
In the what is
The reason is that R3, what? I cannot hear anything suddenly. Are you guys feeling the same thing, or it's only me? It's like soundless. So weird. Oh, I can hear myself. Okay, R3, what I was saying? Can only have. R3 can only have how many linearly independent? Maximum 3 linearly independent vectors. So if you have 4, automatically they are not independent. It doesn't matter how many you have, but the four of them you have, they're definitely not independent. You cannot have more vectors than your space, the dimension of your space. So R3 can have only 3. You cannot have more than 3. That asks us the second question. Well, we know 4 of them are not independent. So how many independent we have? So if 4 are not independent, our next question is, do we have 3 independent? How do you check whether we have 3 linearly independent vectors or not? What do you use, Alvin? Cross one of them out. It doesn't matter which one you cross out. You can cross out one of them, but I'm just crossing out the last one because it looks weird. And then find the determinant for the other 3. So what's the determinant of V1, V2, V3? It is 0 or not 0? This is V1, this is V2, this is V3. 1, 0, 0, 0, 1, 1, 1, 0, 1. 1, 0, 0, 0, 1, 1. So what's the determinant? Instant. You get 0. One, 0, 0. So the right gives you 1. If you look at the left, 0, 0, 0. That's the determinant. 1. So how many linearly independent vectors we have? We found the determinant of the 3 vectors is 1, which is not 0. So how many linearly independent vectors we have? 3. If the determinant was 0, then we could say, well, three vectors are not independent. Then we go and check whether 2 of them are independent or not. So we start from 4, cross out 1, go by 3, 2, and 1. Okay, so we have 3 linearly independent vectors in R3. Do they span the entire vector space? Do they? Yes. Even though we have 4 vectors, but it doesn't matter. We need at least 3 to span the entire set. So we can have more, but less is not allowed. So what's the dimension of our span? The dimension of the span? 3. And you already know the answer for the 5th one. 4 vectors in R3 cannot form a basis. The basis is like foundation. Do all 4 vectors is the foundation of R3 space? No, because R3 has three foundation: x-axis, y-axis, z-axis. So 4th one is an extra one. It's not in the foundation of R3. And the last one we did in our last class, which took a little bit time. So go watch the recording for the answer for this question. Any question on any of these? In the exam, I'm going to put a few of them because they don't require any math, except for the first question, linearly independent. Brendan.
So it's like 1, a line, 2,
1 gives a line, 2 is a 2D plane, and for 3 in R3, 3 in R3, or never mind, it doesn't matter which space you are in. If you have 3, it's a 3D plane. Oh, you have to say non-zero linearly independent. If you have 1 non-zero linearly independent vector, it's a line. If you have 2 non-zero linearly independent, it covers a 2D plane. If you have 3 non-zero linearly independent vectors, they cover 3D plane. If it's a 0 vector, then the answer is false. These are true only for non-zero vectors. Random.
So like number 2, you can do that.
So these are the geometric shape. And all 3 things, they go through origin 0, 0. It doesn't matter which space you are in, which vector space, they all go to the 0, 0 origin. Okay, we have, oh, can I flip my page? And this is the answer table, the answer key. The next question is an interesting one. It says we have 3 vectors in R2. Our x1 is 2, 1, x2 is 4, 3, and x3 is 7, negative 3. Does x1 and x2 form a basis for R2? So instead of having 5 different answers, 5 different questions to answer, they're asking the 5th question directly. You have 2 vectors, x1, x2. Do they form a basis for R2? So what do you need here to answer this question? What do you need to know? What do you need to know?
linearly dependent.
How many linearly independent vector you have? How many linearly independent vectors? So we have 2, 1 and 4, 3. Do you have one linearly independent vector or two linearly independent vectors? In other words, are they independent or they are not independent? When you have two vectors, how do you check? Remember, two vectors is the easiest one to check. When you have two vectors, what do you do? Multiply by a scalar. So if you want to go from 1 to 3, you need to multiply the first vector by what? 3. That means you need to multiply 3 by 2. If you multiply 3 by 2, what do you get? But what do you have? So are they independent? Yes, because it should be 6, 3, but it's not. It's 4, 3. So they don't have any connection. One vector is not a scalar multiple of the other vector. So we have two linearly independent vectors in R2. Do they form a basis for R2? What's the condition for basis? How many independent vectors you need? Exactly 2. Do you have exactly 2 x1, x2? Yes. So the answer is yes. They are not saying from x1, x2, x3, do they form a basis? They are only asking about x1 and x2. If you take only x1 and x2, do they form a basis for R2? Yes, they do, because both of them are linearly independent. Now the next question is asking, well, you have x1, x2, x3. Why one of them has to be a dependent vector? What's the reason?
Because during the R2, like
R2 space.
R2 space, so they have to like cover that. And then again with the next one, it doesn't really like over that's the
R2 needs only maximum 2 of them. If you have anything more than 2, it's a linear combination. That's why. If it was R3, then it's not true. But for R2, it cannot have more than 2 independent vectors. Now, what's the dimension of the span? X1, X2, X3. If you look at all 3, the span of all 3, what's the dimension of their span? What is dimension of the span? What do you look for? What do you look for? Good. So between x1, x2, x3, how many independent vectors we have? 2. So our dimension is 2. We only check that when you look for the basis question. The basis is telling us we have 2. So the dimension of the span, it doesn't matter how many vectors you have, they have to be 2 linearly independent. So we have 2 independent vectors in R2. What's the geometric shape of the span? 2D plane. 2D plane means the entire XY plane. So here's the answer. Oh, for B, we can also answer with a theorem from the book. This theorem is basically saying that if you have a bunch of vectors v1, v2, v3 in your space, which is a spanning set for the vector, then if you have any collection of vectors, it doesn't matter how many vectors you have in your collection, they cannot exceed the dimension of your space. So if you have 3 vectors, it has to be 2. Anything more than 2, you may have 3 vectors, 4 vectors, 5 vectors. All of them will be dependent on the two independent vectors. The next question is very similar, but we have 3 in R3. Our first vector is x1, 2, 1, 3. Second vector is x2, 3, negative 1, 4. Third vector is x3, 2, 6, 4. And then we have extra one, y, which is negative 9, negative 2, 5. Now, the first question is asking, just take the first two, x1 vector and x2 vector. If you,
I'm sorry. I'm sorry, I'm looking at the previous one.
Mhm.
We said that it was a 2D plane, the shape,
Mhm.
but there, on D, it says a line.
it's a typo.
Oh. Alright.
Thank you for catching that. I actually didn't catch it. Let me fix it here so that counts. Place. Yeah. Okay, so take only two vectors, x1 and x2, and then find out is the x3 is x3 in the span of x1 and x2. It means is x3 a linear combination of x1 and x2? Is x3 in the span of x1, x2 means is x3 a linear combination of x1 and x2. It means if you multiply something with x1, x1 plus b, x2, do you get x3? Is it possible? We have an idea how to answer this question.
You could check if there are ways of independent.
Using what?
Sure.
Good job. That's the easiest way. There are many other ways, but the easiest way is just look at the determinant by forming a matrix. If the determinant is 0, that means it is independent. I mean, it is not independent. But if the determinant is not 0, that means the 3 vectors you have in your matrix, all 3 vectors are independent. So we have x1 is 3, no, 3, sorry, 2. We have 2, 1, 3. The next vector is 3, negative 1, 4. And now we are checking 2, 6, 4. Form a matrix with them and find the determinant. So my favorite method, 2, 1, 3, 3, negative 1, 4. We have 2, negative 1, 4, which is negative 8. 3, 6, 3. So 3 times 3 is 9. 9 times 6 is 54. And then the last one is 2, 1, 4, which is 8. So these are right diagonal. And if you look at the left diagonal, so we have 2, 1, 3, which is negative, negative, positive 6. 2 times 6 is 12. 12 times 4 is 48. So negative 48. And then the last one is 314, which is -12.
Positive.
But you're subtracting.
Oh,
So if it's negative, the sign will become positive. If it's positive, the sign will become negative because you're subtracting. So what do you get? 0 or not? Do you get 0? Do you get 0? Did you? Is anyone checking?
I did not. Okay.
Not 0. So what does that mean? Is x3 in the span of x1 and x2? This information is telling us x1, x2, x3 all are linearly independent. So if all three are linearly independent, can x3 be a linear combination of x1 and x2? Of course not, because they're independent. And if x3 cannot be a linear combination of x1 and x2, that means it cannot be in the span of x1 and x2. So the answer is no. Because x1, x2, x3, all three are linearly independent. They do not have any relation. They do not have any combination. Check the y by yourself and tell me the answer. Is y in the span of x1 and x2? It means is y a linear combination of x1 and x2? Hailun?
For x3, are you sure the determinant is not 0?
Alvin, are you sure determinant is not 0?
It is.
It is 0?
It would be the 8 cancel out in type
8 cancel out.
7 on the
This is 60. And this is 50 and 60. That tells us everything else is wrong. If the determinant is 0, what does that mean? Are they independent? x1, x2, x3, are all three independent vectors? No, they are not independent because the determinant is 0. So since the determinant is 0, that means x3 is in the span of x1 and x2. It means, yes, you can find some constant a and b. If you multiply x1 with a and x2 with b, add them, it will turn into x3. So it is a linear combination of the other two. Try it with y. Is y in the span of x1 and x2? It means whatever area you are covering with x1 and x2 is y in that area, or y is somewhere else. So you're going to do the exact same thing. Two, one, three, and 1, 4, and then -2, 5. And then minus 18. Five times to 10. 3 times 3. 9 times 2, 18. 9 times 4 is 36. So what's the determinant this time? Determinant of x1, x2, and y. Is it 0? We have more zeros, -10, -18, -36, -27, -15. So if you add all of them and subtract 16, do you get 0? So is y a combination of x1 and x2? If the determinant is not 0, what does it mean? x1, x2, y, all of them are what? Independent. So all three are linearly independent. So can y be a linear combination of x1 and x2? Nope. So is y in the span of x1 and x2? Nope. So if the determinant is 0, that means they are not independent. So one of them is a combination of the other two. But if the determinant is not 0, that means the three vectors you have, they all are independent. They do not have any relationship, any connection or anything. So if all three are independent, how can y be a combination of the other two? It's not possible because all three are independent. Caroline, you look confused.
No, I get it now.
Right? Okay. Any question from anyone? No question?
So if you have 3 and the determinant is 0, I don't know if you're the first example, you still need to determine about one is or 2 are linearly independent.
It depends on the question. If they're asking to find how many independent vectors you have, then you have to check. But here they're not asking, they're only asking. So B here is asking the x1 and x2 you have, are they independent or not? So if you compare x1 and x2, what do you see? Do they have any type of relation, any type of connection? In other words, is one of them is a constant multiple, scalar multiple of the other one? Nope. So yes, I mean, they are independent. So we found that x3 is not in the span of x1 and x2. So x1, x2, x3, all three are independent. What it tells us about the dimension of the span of x1, x2, x3? 2, why 2? So it's not in the span means it's not dependent, it's independent. So how many independent vector do you have between x1, x2, and x3? But you're just telling me in A that x3 is also independent. Because when you found the determinant, wait. X3 is not independent. X3 is dependent. That's why the determinant is 0. So yes, the answer is 2. Because 3 is a linear combination of the other two. So what's the span? What's the geometric shape for the span? X1, x2, x3 means how much they cover? 2D plane. That goes to the origin. Any question on any of this question we did today?
So if there was one, like if the question was for X1, X2, X5,
Why?
would it be?
Then the answer will be different. The geometric shape will be 3D plane and the dimension will be 3. So y, x1, x2, and y are independent, but x1, x2, x3 are not independent. And we figure out x1, x2 are independent. So 2 independent vector in R3 space covers a plane, a 2D plane, and its dimension is 2. Okay, so we already know the answer for this question, so let me skip. Few theorem from the book. This one you already talked about it a few seconds ago. It says if you have more vectors than the dimension of the space, then they cannot be linearly independent. So if you have 3 vectors in R2, definitely one of them is not independent. If you have 4 vectors in R3, definitely one of them is not independent. The next corollary, which is a statement that follows directly or is an immediate consequence of the previous proven theorem or proposition. It says, if you have 2 sets of vectors, v1 to vn and u1 to um, and you know that both sets are bases for the vector space, then the number of vectors you have in each set, they have to be same. So if you have one vector with one set with v1, v2, and another vector with e1, e2, these 2 numbers, they have to be same. Like you have 2 vectors here, you have to have 2 vectors here. You cannot have 3 vectors for a basis and 2 vectors in another set for a basis. The basis have to have the same amount of vector for the space. Like R2 needs exactly 2 vectors. R3 needs exactly 3 vectors. So it doesn't matter how many sets you have, all the sets, they have to be exactly 2 vectors. Then it says if V is a vector space, then if V has a basis consists of n vectors, then the dimension of the V is n. In other words, if you have a set with 2 vectors, that means it belongs to R2. If you have a set of 3 vectors, 1, 2, 3, that means it belongs to the R3. So the dimension of your space is the same amount of vector you have in your basis. If you have a subspace 0, subspace 0 of the V has a dimension 0. I thought it would be dimension 1, but yeah, it's a dimension 0. If V is a finite set of vectors that span V, then V has a finite dimension. Basically, if you have a set of vectors that span the entire set, that means they have to be a finite dimension. You cannot have a big, huge dimension that doesn't have any countable or any finite number of vectors. So you're in a finite dimension space, not in an infinite dimension space. In order to have an infinite dimension space, then you have to have infinite many vectors in your span. Another theorem, it says the last one. If V is a vector space of a dimension more than 0, then any set of n linearly independent vectors span V. If you have R2, then any set of 2 vectors will span the entire, so V1, V2, E1, E2, or probably S1, S2. It doesn't matter how many sets of vector you have, all of them, they'll be linearly independent. And any n vectors that span V are linearly independent. I mean, basically we already know them because we know in order to be in order to span the entire set, you need to have n many linearly independent vectors and at least n many. This is the summary of that sentence. In order to span the entire space, you need n many linearly independent vectors in your set. So I have a little bit information left, but we're going to talk about that in our next class briefly. Okay, that's all for today. I'm going to post the review sheet. I didn't make it yet. So my plan is to make it tonight, and then definitely before Friday, I'll post it, inshallah. So have a good night, have a good weekend. I see your email.
Oh yeah, I've been trying to get here since like 5, not even 5, since like 4:30. My bus drove right past me. I was like, what? But is it possible for me to get like a late today or something? Or like,
Yeah.
okay, thank you. Sorry.
Bye, Brenda. Maisha, are you okay? Oh, shit. What's it?